Yes, that's right.
Okay, in that case, I'm going to go ahead and click the admit all button. Someone else can admit people who are latecomers. That often happens, but I'm going to click the admit all button now. I think a few people are still marked as still joining. Okay, I think we've achieved a quorum, and those who were in the waiting room have now joined us. Welcome to the Magnetosphere online seminar series. I'm David Sybank here at NASA's Goddard Space Flight Center. Today, we're going to have two early career presentations. I'd like to ask you to mute your microphones. Please place any questions that you have in the chat box. And I'd like to remind you that this presentation is being recorded and that it will subsequently be posted to YouTube for others to see. So with that said, I would like to introduce the first speaker today. That is Gonzalo Cucho-Padin. He's a postdoctoral researcher here at NASA's Goddard Space Flight Center. His doctor's thesis addressed the distribution of neutral densities in the terrestrial exosphere. He used static and dynamic tomographic techniques to infer the exosphere's structure from Lyman alpha measurements by NASA's TWINS mission. But today, he's going to turn his tomographic reconstruction talents towards the Earth's cusps and tell us about his recent efforts to reconstruct the Earth's northern and southern cusps. So with that, Gonzalo, please go right ahead.
Thank you so much, Dr. Sybank. Thanks for inviting me to give this presentation. So the topic for today is three-dimensional reconstruction of ion fluxes in the Earth northern cusp using neural networks. And of course, thanks to Dr. Sybank again, because he's my collaborator on this project. Okay, this is the outline of my presentation. I'm going to start providing you a background and motivation. Because this is a database analysis to investigate the Earth cusp, I have to provide what are those data sources that I will use. Then I will mention how the neural network model for the Earth cusp is constructed. I will show some results. I will finish providing conclusions as well as future work for this project. Okay, for the background and motivation, I have three main questions. One of them is related to the day-side magnetic reconnection. So this is the principal mechanism to transport mass, energy, and momentum from the solar wind to the inner magnetosphere, ionosphere system. The day-side magnetic reconnection is probably one of the main objectives for the magnetospheric community. And for those who are not familiar with this topic, here I have an animation in which we can observe southward interplanetary magnetic field that comes from the sun, some particles here that are solar wind ions or particles, and they are moving and they merge with the terrestrial magnetosphere. At this point, we have what we know as the day-side magnetic reconnection, and the trapped ions in the IMF can enter to the Earth system. So what we need to know is how often, where, and when the day-side magnetic reconnection happens. For this, we can do it by using in situ observations that in fact we have. MMS mission, which is a NASA mission, observe these events, unfortunately not that often to analyze the dynamics of the magnetic reconnection. So now, what is the Earth cusp? The Earth cusp, in fact, we have two of them, one in the northern and the other in the southern hemisphere. The cusp is this region, is a funnel-like region where the solar wind plasma precipitates to Earth from the magnetic reconnection sites. In this plot, the magnetic reconnection sites, it's happening here in this X. This is typical for a southward IMF. And then the trapped ions can enter from the IMF to the internal part of the inner magnetosphere. So why do we need to study the Earth cusp? It's because the ion dispersion within this region is connected or can provide information regarding the day-side magnetic reconnection, and that's what I'm going to explain in my next slide. So now, how can we investigate the Earth cusp? We have two ways. The first one is based on in situ observations, specifically using ion and electron spectrometers. And here I have listed some of those missions with this instrument that crosses the cusp. Also, we can use remote sensing techniques in which the data is acquired from a distant vantage, and usually is an image. In this case, there are 2 missions that will be launched in a couple of years, 2 or 3 years, SMILE and LEXI, and they will observe sub-X rays. The sub-X rays are generated through the interaction, charge exchange interaction between solar wind ions and the exosphere, the terrestrial exosphere. That interaction creates sub-X rays that can be obtained in an imager, and then this image can provide information of the densities in the magnetosheath and the cusp, and also the dynamics, movement within this region. Okay, in this slide, I tried to explain this connection between what we can observe in the cusp and the day-side magnetic reconnection. For this, I have 2 cases. The first one, here I have a case in which we have a southward IMF. When we have a southward IMF, we have 2 conditions. The first one is that the day-side magnetic reconnection tends to happen near the subsolar point or the equatorial plane or at low latitudes. But also the southward IMF induces an electric field. As you can see here in this direction, it gets out from your screen. Together with the magnetic field lines here, they will create a drift or convection or movement of ions in this direction from the day side to the night side, or from low latitudes to high latitudes. So those ions that were trapped here are going to go through this path and try to enter to the terrestrial system. In this sector, the ions will have different energies. Those with higher energies will impact the Earth at low latitudes, while those with lower energies will be impacted by the convection and they will be moved towards higher latitudes. In sum, high energies will impact the low latitudes and low energies will impact high latitudes. So how can we observe that in the Earth cusp? Well, what I'm showing you here is a measurement from cluster. It was taken when the satellite was moving from low latitudes to high latitudes. This green square and red square indicates the positions. And in this plot, this is called an spectrogram. This is specifically for ions, specifically for protons. And the x-axis here is time, but it's also related to location in latitude. The y-axis are energetic channels. The top row are the high energy, and the bottom row indicates the low energy. The colors here indicates the flux, is basically how many particles I have for a given latitude and for a given energy channel. So, as I said before, the high energetic ions that are coming from the day-side magnetic reconnection will be located at low latitudes, and the lower energetic ions will be located at high latitudes. So this pattern, it's called the ion dispersion. This is a typical signature when we have a southward IMF. Now, when we have the other case, when we have a northward IMF, the magnetic reconnection can happen at high latitude, while the electric field is induced in the other direction. Now the drift goes in the opposite direction than the previous case. Now it goes from high latitude to low latitude. And what I am observing here is something similar. The satellite is still moving from the low latitude to high latitude. In this case, the high energy ions will impact the high latitudes first, and then the low latitudes, the low energy will impact the low latitudes due to the convection. So this pattern is shown here. This is a different distribution. This is also called ion dispersion, but this is the reverse ion dispersion. So if we do the analysis of these structures, we can identify where the day-side magnetic reconnection happens, but also we can investigate what is the transfer of mass by looking at the values of flux here at the cusp. So the research objective of this project is to generate a fully data-driven model of the Earth cusp, in this case, specifically using cluster data. So we are going to create a regression model that will allow us to observe the three-dimensional structure and spatial distribution of proton flux. This model will have this structure. We have this part, which itself is the model, and is based on a neural network system. And it will have inputs and outputs. The inputs we have selected as solar wind parameters as well as geomagnetic indexes, and it will predict ion flux in a given point in the space. but also we need to have some information to train this neural network. That information is called the target or the observed data or the in situ measurements from cluster, which is also ion flux. In the future, and this is not done here in this project, but in the future, we plan to make comparisons with magnetospheric physics-based models. I have listed some of them here, and the reference explain much better each of them. Okay, for now, I'm going to explain what is the data that I've been used for each of these components. I'm going to explain first the target, and the word that I'm going to use is the target vector. That is the unit of data that I'm going to use in my presentation. So I'm going to start explaining what is a target vector. The target vector will be comprised of cluster mission data. The cluster mission data has 4 spacecraft featuring a tetrahedral formation, as you can see here. And each cluster has a name, but I simplify that name with these letters and numbers, C1 to C4. Each spacecraft has around 11 different instruments. In this case, I'm going to use the cluster ion spectrometer composition distribution function, or SysCodif, since they provide ion flux spectrogram. The SysCodif is available only on 3 of these sensors, C1, 3, and 4, and they provide information in the range that goes from 25 to 35 keV, divided into 31 energy channels. Also, the data that I'm going to show you here is omnidirectional proton flux. Probably in the future, we will use electron flux or parallel and anti-parallel proton flux, but in this case, we're going to use just omnidirectional. In these 2 plots, I'm showing the a cluster, an example of a spectra obtained by cluster when it was moving from low latitudes to high latitudes. This is the cluster path trajectory. The path is a 3-dimensional path. However, it was projected to this XZ plane in SM coordinates. It goes from this green square to this red square. And what I'm showing here are just samples of the flux for 3 different energies, 10, 1, and 0.1 keV. These 3 energies are indicated by these 3 arrows here. And this is the typical spectrum that we will use in our analysis. So we can identify 2 sections, the inner magnetosphere in this part, probably the ring current, and here we can identify the air cusp. So what is important to mention here is what is a target vector, which is 1 column of this spectrum. 1 column of this will contain 31 energy beams. Okay, now I'm not going to use all the cluster data. I'm just interested in doing the analysis for the air cusp. So for that reason, we have created a kind of a spatial filter. This spatial filter is called a region of interest, which is a spherical sector in solar magnetic coordinates. You can observe here how it looks, and these are the dimensions for this region. We investigate through the literature as well as doing the analysis in the data to verify that these boundaries are correct, and we can have the air cusp within the region of interest. Now, in these plots, you can observe the encounters for cluster 1, 3, and 4 with the region of interest. So each data point here is a target vector and will contain 31 energy beams. The colors here indicates the years in which that data has been acquired. So for cluster 1, we have data from 2001 to 2004, and from cluster 3, we have data from 2001 to 2009. Now the plots, again, it projects all these 3-dimensional points into a 2-dimensional plane, just to show you the distribution and the coverage in the radial dimension as well as the elevation dimension, the theta. In this plot here, I just projected all these 3D points again to the XY plane to show you the coverage in the azimuthal dimension. However, as I said, these are 3-dimensional points, and I can tell you that the data still exhibit spatial and temporal sparsity. And that is the reason because we're going to create a regression model, because it is a kind of sophisticated interpolation. And even that we don't have a great coverage of all this region of interest, we can still predict some values everywhere in this space. Now I'm going to describe the input vector. The input vector is created with the OmniWeb dataset. We have 8 different values, 6 from solar wind data. We have used magnetic field, By and Bc, velocity, density, flow pressure, and electric field, and geomagnetic indexes like symmetric age and the auroral electrojet index. We used the highest resolution that we can obtain from OmniWeb which is 1 minute. And also we have a time history of 30 minutes. So these authors here mentioned that the response of the aircast to solar wind variations could happen instantaneously, or they can take up to 30 minutes. So we have taken these 30 minutes as our threshold. So this 30 minutes means that we will have, if we have a target vector located at this point, we will go back in time for 30 minutes, and then we will collect all this data. Also, and unfortunately, the OmniWeb dataset features some gaps in the data that should be, we have to do an action for them. In this case, when the data gap is smaller than 5 minutes, we applied a linear interpolation, and when it's greater than 5, we just discard that data set and the corresponding target vector. So all this point here creates the input vector. We have 240 elements in all of these. We have 8 multiplied by 30, we have 240, but additionally, we have 5 more that I will explain in my next slide. So this is the neural network that I have created to create this model of the aircast. So first of all, I'm going to explain what are the inputs and outputs, and I'm going to start with the output. Well, not exactly the output, but the target vector. The target vector is what we need to train this neural network. The target vector will have the 31 energy beams, values of fluxes. This is the length of this vector. And in the input, as I said, we will have 240 elements. Some of them are from solar wind, some of them are geomagnetic indexes. And as I said before, we have 5 additional elements. The first 3 are related to the position of the satellite, of the cluster satellite, when it was acquiring the target vector. The next 2 are related to the dipole tilt information. Because we have used the SM coordinate system, the z-axis is the dipole. So to have more information about this dipole, and specifically the tilt of the dipole, we need to make a comparison with another reference. So that other reference is the GSC coordinate system, the geocentric solar ecliptic, which is fixed in the solar Earth system. So we have calculated this phi and theta, or azimuthal and elevation angle, of the ZSM with respect to the ZGSE. What you can observe in the center is, as I said, the neural network. This is a multi-layer perceptron that it has 2 hidden layers and 1 output layer. I have applied an optimization process that I will explain really quick in a couple of slides. So what you can observe here is the hidden layer. This is a typical neuron with weights and bias that are unknown at the beginning, and after the training process, we will have these values. This ReLU is the activation function, and this is the same structure of the neuron that is used in all the system. So the number here is the number of neurons per layer. So to train this neural network, I have to create data sets. Data sets that are typically known and testing, training, and validation sets. So the way to do this is complicated, but in this case, we have adopted a different technique that usually is taken. Usually, the data is taken randomly, but in this case, we organize the data first. What you can observe in this plot is the total target data set. Each column here is a target vector, and we have divided this into encounters. So each block here is an encounter of one cluster with the region of interest. In some cases, we can observe the ion dispersion. In some cases, no, but it's good because not having dispersion or not having the aircast in this measurement, it's also information. So these encounters, as I said, are with the region of interest, and this division help us to create these data sets. What we have done is to generate these data sets using random encounters, or randomly select the blocks that we have here. So let me tell you why we are not using the random selection. So the random selection means that I can take one vector from this block and one vector from this block and create a data set with that idea. However, when we take a random vector from here, what we are doing is to forget or leave the information that can be there just because the data was taken sequentially. So, and that also can produce data leaking, that can also produce overfitting. So as I said, in this case, we first create this kind of blocks, and then we randomly select blocks to create the training, testing, and validation sets. And this percentage here indicates how much data we have in each of these training data sets. Then I have in this table the number of target vectors per spacecraft and the number of encounters with the region of interest per spacecraft. We have at most 416 encounters, and I want you to keep in mind this number because I'm going to compare with other missions that in the future will provide a humongous number of encounters. But for now, this is the highest number that we have. And because this number is small, what we have decided is to use all this data together to create a single model, which means that we have to assume that the sensors are identical. They are not identical. The energy beams are centered at different energies for each spacecraft. However, they are quite close. So our assumption is still valid, and we have used around 440,000 target vectors to create this model. So as I said before, this model has been optimized. This optimization requires to select hyperparameters. Those hyperparameters are listed here. So those hyperparameters are the number of hidden layers, the number of neurons in the hidden layers, the activation function, and additional parameters that are also needed to create an efficient model. So what I have to do is to select a range for all of them and use a tool. In this case, I have used the Keras Tuner, and then Keras Tuner will provide us the best selection. What I show you here is the best selection. So, and that's what we have used to show you the results that are coming in my next slide. Okay, so I'm going to show you some results first about the model performance. So this is the typical plot that you will observe when you have a machine learning regression model. And this is a comparison between the output vector, which is the output of my system, and the target vector, which is the observed data, the in situ measurements. The output vector and the target vector, as you probably now know, they have 31 energy beams. However, I have no space, and I cannot show you all those 31 plots, and I should have 31 of them. However, here I'm just going to show you 3 of them for 3 different energies, which are 10, 1, and 0.1 keV, the same energies that I've been using in all my presentation. So one point here indicates that the observed data was, let's say this one, was 6. However, my model was identified this value as 1.5, which means this is an underestimated value. Also, the color indicates how many of these pairs I have. So I have few of these because this is blue. So what I'm expecting is that most of my points here will be located around this line, which is the moderate equal observed line, which indicates, let's say, perfection in the prediction. However, that is usually not possible in this kind of regression models, but we expect to have most of these points here. And that's what we have. The red section indicates that many of them are located along this line. Also, the yellow color indicates that. However, we have to acknowledge that there is an underestimation around this region, around the flux. Remember, this is the log 10 of the flux. Around 4 to 6, we have underestimation in all the cases. And also we have overestimation of the model when the log 10 flux is equal to 0, which is this section here. So the observation says that it's 0 for a given point in the space, 0 flux. However, our model presents a higher value. So that is the results of overestimation. So all these plots were done with the training data set. The training data set was used in the training process, so the model knows this data. As you can see, it's not that perfect. This case is for the testing data set. So this data set never passed in the training process, and everything here is just prediction. It was never used in the training process of the neural network. So still we have the same patterns. We have the underestimations in this region and the overestimation around the log 10 flux equals 0. And also we have a good agreement in terms of having many of these points around this line, at least for this region of flux. Additionally, we have calculated some performance ratios like the Pearson correlation coefficient and the mean absolute error and the symmetric signet percentile bias. In this case, I'm just going to focus in the test because that was not part of the training process. We have a 0.81, which is typically a good number for the R-square value. And I just want to focus in this one, which has a negative sign. This performance ratio is well explained in this paper, and it indicates if our model tends to underestimate or overestimate just by looking at the sign. In this case, this -2 indicates that our model tends to underestimate the real values. Now I'm going to show you some results of proton flux prediction. In this case, we can observe the proton flux. It was acquired by cluster when it was in this position. I'm using the similar format I showed you in my previous slides. And here is the predicted proton flux. So here I have two features that I would like to explain. The first one is the smooth pattern in machine learning-based regression models. This is a typical result that we should expect when we are using this type of systems or models, this kind of smoothness in the signal. And that is part of the training process. So now the different acquisition rates from instruments and data sets are creating another feature in my plot. So you can probably observe here that we have a line or a kind of block that are quite similar, and that is repeated in all the structure. So the data from OmniWeb comes every 1 minute, while cluster is taking data every 4, 8, or 16 seconds, depending where cluster is located in the magnetosphere. Within the air cusp, the data is acquired every 8 seconds, which means that there are 7 samples here that will be used the same input vector, the same OmniWeb data. And that's the reason because we have these plots and they are quite similar because the only variation in this input vector is the position of the satellite, which in 1 minute is usually negligible. So what I'm going to do next is to compare the rows for 3 energies from 3 energy beams that are indicated by these 3 lines, and they are here. So again, I'm using the same energy beams, 10.1 and 0.1 keV. And as you can observe here is in blue, the observed data, and the red line is the predicted data using our model. So there are several features that I would like to mention here. The first one is that the model predicts the general trends, or the low frequency component. When we have a flux enhancement, the predicted value try to provide that enhancement too. When we have a flux depletion, like in this case, the model also can predict that trend, but we acknowledge that the model cannot reproduce abrupt changes like we can observe here. So there is a kind of delay in this, in the prediction, and also the model cannot reproduce the high variability in the signal that you can observe here that is probably caused by noise in the measurements. Also, we have observed some patterns in the inner magnetosphere, which is located here, and we go back to the signal. You can observe this pattern here in the in situ observation, and this pattern probably responds to a longer time history of the input vector. As you can remember, I have used a 30 minutes time history, and that probably can take more than 30 minutes. But this is not part of the study. So we are just studying the air cusp, but still I just wanted to mention. Okay, now I'm going to show you some 3-dimensional results for this using this model. So this is the input data that I'm going to use. This is the reconstruction spatial domain. I have reduced this radius. It started at 2 RE, but now it will start at 4, just because we have more data and the uncertainty in that region will be smaller than in other cases, so it will start at 4. So the 3-dimensional structure is complicated to show, so what I have done is to cut or provide some slices. In this case, I'm going to provide just the meridional plane of the air cusp. What you can observe here is the flux at every point in this meridional plane in the range I have described it before. And here, what I have done is to observe specifically these 2 energy beams, which is these two are part of the air cusp population. We're not going to find particles of 10.5 keV in the air cusp. So I'm just going to do the analysis of these two. And here you can observe the structure of the air cusp. And additionally, what I have done is to identify a kind of center of mass with these green lines. So you can observe that at 1.2, we have this line around 64 degrees, and at 0.14, we have this line around 66. So this variation in the location of this kind of center of mass is a response to the VC. In my input data, I have a Vy that is negative, but also we have a Vc that is negative in the last, let's say, 10 minutes. So Vc negative is a software IMF. I'm expecting some kind of dispersion, and that is what I'm observing here. If you remember in the ion dispersion, when we have a software IMF, when we have a lower energy, it should be located at a higher latitude. And that's what we observe here. The center of mass is located at 66, while this one is located at 64. But we can observe this pattern also in a different plane. In this case, I have this transversal plane. This is a spherical surface that has been projected to the XY plane. Again, I'm going to do the analysis for these two energy beams. We can observe here something even more interesting, because we can observe that this kind of center of mass is not only located at a lower latitude in comparison with this, which is the response to the VC, but also it is located in a near dome, which is also a response to Vy. Vy, it's also creating an effect in the position of the air cusp, and it's moving the higher energies downward, which is what we can observe here. So these are the kind of physical behavior that we are expecting in the air cusp, and we are obtaining these values only using data from cluster. So that is promising for the future and to use these kind of models. So now, and this is probably the final slide about results, I'm going to show you a video. Here I have inputs. Those inputs were obtained from the OmniWeb dataset. They were obtained with 1 minute resolution. However, I have done an interpolation to have a 3 second resolution. And the dot that you can see here is the moment in which this data will be created. Again, I'm showing the meridional plane for the 3 same energies. This dot will be moved. And again, as I said before, the input vector used 30 minutes. So 30 minutes of this data will be used to create this plot. Here I'm showing an ion spectrogram that is showing the values of energies with respect to latitudes. The latitudes go from 25 to 75, and the resolution is 1 degree. This spectrogram is obtained at this region when this black dotted line is located. The radius for this is 5 RE. This is geocentric distance. And let me just run this to see what is this, how the structure of the air cusp change. We have observed that in the 1.2 keV, which is part of the population of the air cusp, we have a response to the VZ, and in this case it's quite clear. I'm going to make that comparison just in a moment. So I have to mention that the VC goes from negative, this is a software IMF, it becomes positive, becomes a northward IMF, and then it changed a little bit in the last 30 minutes. So you can observe in the 1.2, the location of the air cusp when we have only a software IMF, and how it changed when we have components of northward IMF. So what we are expecting is to have changing the latitude of the air cusp, and as you can see, it is moving forward or to higher latitudes. So this model is useful to investigate this kind of physics that we are expecting in the air cusp. Also, it can provide quantification of this. For example, in this case, I have done the analysis only for Vy and Vz. The analysis can be done also for Vx and for the density or for the pressure and for any of the inputs and that will be part of this future work. So I'm just going to finish this by reading these conclusions. We have developed a neural network-based model that can estimate the time-dependent and three-dimensional structure of the proton flux, specifically for the northern air cusp. And all of the reconstructions of the ion flux are smooth, which is, as I said before, a typical characteristics of these regression models. The results reveals a good agreement with the dispersion theory, specifically in response to By and Bz, as I showed you in my slides. So the future work includes the analysis of the contribution of each solar wind parameter. I have done only with By and Bz, but the density and velocity can also contribute in the spatial structure and density of the ion flux, and that's what is coming next. Then we would like to investigate how to use this parallel ion flux and also the electron flux, since they can provide and can improve our results, since they provide sharp features for the identification of the air cusp. We also would like to use the ion spectrometer on board the DMSP mission, which has a high number of encounters, although it's limited to low altitude. The analysis that we have done here with cluster goes from 2 RE up to 12 RE, which is the mid and high altitude air cusp. DMSP can be helpful to analyze the low altitude. And finally, there is an upcoming mission that is called Tracers that will have 2 satellites at LEO orbit, and they will take more than 3,000 air cusp encounters per year, which compared with the 400, this mission seems to be super helpful for this type of analysis, of this database analysis. Okay, that's all what I have, and if there is any question, I would be more than happy to answer them.
Super. Thank you very much, Gonzalo. We're running a bit late, but we're going to ask 2 very brief questions, and hopefully the answers are equally brief. The first question is from Eric Lund, and he asks, is it plausible that the overestimations at nearly 0 observed flux are due to data dropouts?
Okay, so that is a complicated question. I think the overestimation is happening when we have this type of structure in the data, which is related probably, I don't know exactly, probably to the noise. When we have this high variability that we are not expecting, like in some cases, for example, we can observe that is overestimation. But yes, I'm going to analyze this comment and try to investigate more on this topic.
Okay, thank you. The second question is from Rong Ploi Fan, and the question is, how did you feed in the geomagnetic indices as input? Are they time shifted to match the OmniWeb data? Or perhaps it's vice versa. Are the OmniWeb data time shifted to match the geomagnetic indices?
Okay, all this data is put together and let's say in parallel to the neural network. So this VYT is just a vector of all of these points. So now I guess I understand what is the question. It's like, how did you put a kind of weight to indicate which one is first and which one is second? That is something that I'm not doing, and I'm expecting the neural network to obtain that information. As you know, each of these inputs will have a W and B. So those weights, and this is something that I will do in the next phase of this project, can indicate what is the importance of each of these values. But in fact, I'm not including at this point any additional information regarding the time. So I'm expecting these Ws can provide that information. Some of them probably, I'm expecting that the last values have a really small W, while the first one has a high W. And the W are those weights that are connected to the inputs.
Okay, and you use the time-lagged Omni data set, is that right? Brought to the Balshark?
Yes, exactly.
Okay, thank you very much, Gonzalo. I would like to turn the microphone over to Jason Schuster, who will introduce the next speaker.
All right, thanks, David, and thanks for a great first talk. And yeah, in the meantime, Alexander, feel free to work on sharing your screen, and I'll give the next introduction here. So yeah, we're very pleased to have our next early career speaker, Dr. Alexander Shane, who's a postdoctoral associate at the University of Colorado Boulder. He received joint PhDs in climate and space sciences and scientific computing at the University of Michigan in 2022. And his research interests include numerical modeling, data model comparisons, electron transport, and wave-particle interactions. And outside of the office, as a fun side note, he does enjoy playing soccer, disc golf, and even chess, which is one of my favorites as well. So with that, feel free to take it away, Alex. Oh, and by the way, you might still be muted, so make sure you can unmute there.
Yes.
There we go. Thanks.
Yeah, thanks, Jason. And thanks for the invitation to the seminar. I'm fairly new to the radiation belt Earth community. I did my PhD on Mars. So I appreciate the opportunity to show off the cool science we're working on. Let's get this. There we go. I'll begin my talk with a brief high-level overview of radiation belt particle precipitation. I'll then discuss our current knowledge on electron lifetimes in the radiation belts, discuss the precipitation loss fraction, and radiation belt contribution to the radiation environment at aviation altitudes. That will set the stage for our science questions. The work is currently ongoing, so I'm not going to be showing any significant results today, but I will discuss our methodology of how we plan to create global maps of precipitating electrons and how we are going to use those to address our science questions. So the dynamics of outer radiation belt are complex. There are a variety of source and loss processes that act on the particle populations. Electrons are ejected into the radiation belts from the magnetotail during substorms and geomagnetic storms, and are then locally accelerated up to relativistic energies by wave-particle interactions, chorus, His, EMIC, etc. The flux of relativistic electrons can increase by a few orders of magnitude during a storm, and then slowly decay back to their nominal values over varying timescales, depending on location and energy through various loss processes. Loss to space and loss to the atmosphere are occurring concurrently, and the net effect of source and loss processes leads to a highly variable environment in both space and time. And wave-particle interactions are the primary driver of electron precipitation. And the altitude at which different energy electrons deposit their energy varies. And radiation belt electrons typically deposit their energy between 40 and 100 kilometers, so below the ionosphere, which leads to chemical changes in the neutral atmosphere. These particles create odd hydrogen and odd nitrogen, HOX and NOx, which assist in the destruction of ozone. And so a global picture of radiation belt electron precipitation will deepen our understanding of the radiation belts by quantifying the variable contribution of loss to the atmosphere. So an accurate quantification of electron lifetimes is important for a couple of reasons. Number one, it helps us understand the dominant physical processes of the radiation belts. Like I just mentioned, radiation belt particle precipitation occurs due to a variety of wave-particle interactions. These waves pitch angle scatter electrons into the bounce loss cone, allowing them to reach altitudes to interact with the upper atmosphere and ionosphere. And the timescales of interaction between wave and electron depends on the wave mode. Therefore, the electron lifetime provides some insight into what the dominant physics are. Electron lifetimes are used as a parameter in radial diffusion models, and accurate lifetimes are needed for models to reproduce key features in the data. And then from an operational point of view, electron lifetimes inform us about how long after a storm the radiation environment is enhanced and the potential risk to spacecraft. So electron lifetimes are typically calculated as the E-folding time of the electron flux decay. This is a plot from Claude Pierre et al. 2020A, and this is Van Allen probes data. And they took daily and azimuthal averages as a function of energy in L shell and fit exponential decays to the time series. And so this time series is for an L shell bin of 4.65. I forget how wide that bin is, but I think it was about 0.25 L. And for energy of 467 keV channel. And the identified lifetimes are in red. You can then perform this calculation for all energies in L shells, and they summarize the results in this plot here. And you can see long lifetimes in the inner belt, very sharp gradient into the slot region, and energy-dependent lifetimes at pretty much all L shells, indicating the different physics important for different energy electrons at any given location. So typically, previous estimates of electron lifetimes have been calculated theoretically from diffusion coefficients, and then often compared to in situ measurements, such as Van Allen probes, like what we saw on the last slide. Electron lifetime estimates from in situ measurements are accurate when assessing the risk to spacecraft. However, from a particle precipitation point of view, these lifetimes do not quite reflect the true rate of electron precipitation into the Earth's atmosphere. The change in flux is due to multiple source and loss processes, which cannot be easily disentangled, often contributing to maybe a slight overestimation of the electron lifetime. You also have both loss to particle precipitation and loss to space, either from magnetopause shadowing or radial diffusion. And these are also taken into account into lifetime calculations, and it is not sure which loss process dominates. It should be noted that in the lifetimes calculated by Claude Pierre, like on the last slide, magnetopause shadowing was minimized due to their criteria that a decay needed to be 5 days or longer. And we've had few estimates from low Earth orbit where the precipitating population can be directly measured. There's been some studies using SAMPEX and Demeter data. Recently with Elfin, really cool data set showing up in the top right, just a comparison of lifetimes calculated from the Elfin data set compared to theory EMIC waves. However, a global map of precipitating electron flux from LEO will allow us to estimate electron lifetimes while isolating the physical processes that cause electrons to precipitate wave-particle interactions. Another thing we can study with global maps of precipitating electrons are the precipitation loss fraction. So a comprehensive estimate of the fraction of radiation belt electrons that are lost to the atmosphere has not yet been calculated. It's generally thought that magnetopause shadowing dominates electron loss during dropouts. And modeling results do not always accurately predict these events well. Furthermore, there are studies that show that atmospheric loss may be the dominant loss channel, and that could even be dependent on L shell and energy. And so on the plot on the right, I'm showing all the color is differential energy flux. And we're looking at from top to bottom, RBSP, GPS, and POES. So kind of going from the highest altitudes down. And we see at the dash red line that RBSP and GPS both observe a dropout event in the around 4 MeV energy channel. And at the same time, at low altitudes, 800 kilometers, POES. Now this is a little different energy channel than what GPS and RBSP are measuring. It's the integral energy channel above 287, but you see enhanced precipitation at the exact same time. And so this precipitation at high L shells may sometimes be otherwise attributed to magnetopause shadowing. And this event kind of prompts the question is what fraction of electrons that were lost in this dropout precipitated into the atmosphere versus lost to space. And so previous estimates of this loss fraction are highly localized and focused on single events and maybe a very narrow energy channel as well. And so we don't have a good kind of baseline to compare specific events to. Another effect of particle precipitation is the radiation environment, especially at aviation altitudes is of primary concern. And it's generally thought that this radiation environment is due to galactic cosmic rays and solar energetic particles. However, recent measurements have suggested that the radiation belts may have a significant contribution. And this contribution is not directly from the electrons, but from the bremsstrahlung X-rays that those electrons produce. Those bremsstrahlung X-rays are able to penetrate to lower altitudes than their parent electrons. And so on the right, I'm showing a plot from Tibisco et al. 2018. And this is the dose rate on the y-axis versus L shell. And the solid red and black lines are the mean and median GCR plus relativistic electron precipitation, REP, contribution, the L shell profile at aviation altitude. And all of the dots highlighted by black circles that we can see up here, these are all noteworthy events that the authors pointed out they think could have indicate that the radiation belts have a more significant effect than previously thought. They saw that the GCR or the radiation levels went from the nominal GCR background, increased by about a factor of 2, and then went back down to normal values. And they said that this is consistent with the bremsstrahlung beam. but we don't have a global contribution, and we don't know the spatial and temporal variations of the radiation belt contribution to the radiation at aviation altitudes. That has not yet been quantified. And so that brings me to kind of the 3 science questions that we're interested in, is how do electron lifetimes from LEO compare to previous estimates from Van Allen probes and theoretical predictions? What is the global precipitation loss fraction? And what is the contribution to the radiation environment at aviation altitudes from radiation belt electrons? And so we are going to answer these questions with global maps of precipitating electrons. And we'll be using the POES data set to build our global maps. I think Josh gave a recent talk about this data set, so I won't go into too much detail. But POES is a constellation of 6 satellites at the moment at 820 roughly kilometers altitude in polar orbits. They each have 2 telescopes that measure 3 integral electron energy channels, and Josh and his crew apply a best fit linear combination of 4 spectral shapes. And then they integrate over the bounce loss cone, and the resulting data set is a time series of energy spectra of precipitating electrons. And so here's a global map of 12 hours in February of 2019 of POES data. And the color of each data point is the integrated total energy flux. And the outer radiation belt is sampled quite well. However, there are many gaps in this map. And here I'm overplotting contour lines of L shells 2, 4, and 7. And you can see that most data gaps are at L shell less than 2. However, regions do exist in the outer radiation belt region where standard interpolation methods might not capture the true precipitation distribution. I think the delta MLT can get up to as high as a delta MLT of 1 between POES data sets in a given L shell. And so we are working on using another LEO data set to sort of help us fill in these gaps. And that data set is the REACH data set. REACH stands for the Responsive Environmental Assessment Commercially Hosted, and it's on the Iridium NEXT satellites. And so 32 of the Iridium NEXT satellites have 2 dosimeters, and they have 6 flavors of dosimeters, where each flavor has a specific electronic threshold. And so they measure different integral energy channels of electrons and protons. And there are 4 model types. So model is a distinct combination of 2 of these flavors. They measure the radiation dose rate due to precipitating electrons and protons. And we are using this satellite constellation to fill in the gaps of POES, and more specifically to infer the spatial variability between POES measurements. So 14 of the 32 REACH satellites have the XW flavor combination, where the X dosimeter measures the dose rate due to electrons with energies greater than 780 keV and protons greater than about 12 MeV. And the W flavor dosimeter is insensitive to electrons. It responds with like less than 1% efficiency compared to X, but with a similar proton response, about greater than 12 MeV. And this means we can use the W to subtract off the proton response of X to isolate the radiation dose rate due to precipitating radiation belt electrons. So here is the same 12 hours, but of REACH data. And you can see that it is a much more complete map. Here again is the POES map for reference. And so we are going to use the REACH data to fill in the gaps of the POES map. Here I'm plotting POES energy flux on the left and REACH dose rate on the right. This is X minus W versus L shell. And the color of each point is the geographic longitude. And this plot is simply here to show the similarity in the spatial variations of the 2 data sets to supporting our methodology. So how are we going to perform this interpolation? Well, first, we are going to interpolate REACH data across the globe. Because it has better coverage, you're not interpolating greater distances between 2 points. Now here we are using a simple nearest neighbor interpolation, and you can see there are a lot of artifacts present in this map, and we're currently working on looking at radial basis functions, spherical harmonics, a better interpolation method to get a smoother and more accurate picture of the REACH dose rate. After we do that, we will bin the POES and the REACH data by L shell and average over latitude. And the result should be 2 lines of flux and dose rate versus longitude. And we'll use the dose rate as the trend line to infer the POES interpolation. And then because that interpolation is done in integrated energy flux, we will go back to the energy spectrum by using a linear combination of the two POES interpolation points. We'll do some validation. We have two methods we want to do this with. One is to use ALFN data. However, ALFN is at, I believe, 500 kilometers. So there will be some necessary shifting, modeling of the distribution down to ALFN altitudes. And another validation we can do is similar to Gonzalo, is reserving some of the POES data set as sort of a test set to then compare our interpolation to the actual data observed there. And we should, at the end of that, have global maps of electron precipitation from September 2018 to December 2019 in 12-hour intervals. And that time period is chosen because that is when the XW coverage is complete. So some methodology caveats. The proton response is not exactly the same between the two. I think actually their X measures a slightly larger integral energy channel than W, and so you may have a slight overestimation of the electron dose rate. That shouldn't matter for a couple of reasons. One is we're not concerned about the true dose rate, more about the spatial variability. And in the outer radiation belt, X is orders of magnitude larger than W. So here's a plot from the REACH dataset README that is plotting L shell on the x-axis and the dose rate on the y-axis for a couple of days. And the X is the blue dots are the X dosimeter measurements, and the orange dots are the W dosimeter measurements. And you can see that in the outer belt, the proton measurements sort of form a background, while the electron measurements have a clear peak. However, if we are interested in doing any detailed science in the inner belt, say L less than 2.5, we will need a more sophisticated subtraction method to isolate the electron dose rate. Another methodology caveat is the pitch angle sampling of REACH. The sensor is looking at different pitch angles in the same location versus northbound versus southbound pass. So on the left are maps of the same days. However, the upper plot is the northbound and the bottom plot is the southbound. And you can see certain regions, especially up here around longitude 0, latitude 60, in the radiation belt, that the southbound has a much higher and much wider radiation belt region. And so that correction needs to be done because we are concerned about spatial variability, and this will artificially induce some spatial variability in the REACH maps. And then lastly, when we do our conversion from integrated flux back to energy spectra, we are using a linear interpolation between the two closest spectra, and that is assuming that the energy spectrum will vary smoothly between those 2 points. The largest gap, like I said, is about 1 MLT, but it is typically smaller. But that is an implicit assumption that we will be enforcing on this data set. Now, some science caveats. Wave-particle interactions are not the only driver of precipitation. I claimed earlier that electron lifetimes calculated from LEO will isolate wave-particle interactions is not entirely accurate. Field line curvature scattering can be important at times, and this occurs when the gyro radius of particles becomes comparable to the field line radius of curvature. So this effect is more prominent for high-energy particles and during times of a stretched magnetotail. So here's a plot from Tu et al. In 2014. On the left is a proton unaffected by this effect. And on the right is a proton 500 MeV, whose trajectory is altered from the traditional view due to field line curvature scattering. This effect will scatter particles into the loss cone. And there is a paper by Artemiev in 2013 that found that it will increase precipitation, but it cannot completely scatter electrons into loss cone just due to the time that electrons spend in the scattering region compared to the lifetimes of electrons due to that process. Recently, Campanolo published a paper looking at precipitation events and identifying them as either wave particle scattering driven or field line curvature scattering driven. And they found that I think 90% of events had signatures of both. And that typically happens because wave scattering occurs at the same time as a stretch tail during active geomagnetic storms. We do not believe it will influence our calculated electron lifetimes because it is so localized in space and time, such as microbursts and other very highly localized precipitation events. Another thing that we need to consider is atmospheric backscatter, that a fraction of lost cone electrons don't actually deposit their energy on their first bounce, but they backscatter, and it might take a couple of bounces before they do. So here's a plot by Marshall and Bortnick in 2018, just showing as a function of input pitch angle. These were test particle simulations, the fraction that were backscattered, I should say Monte Carlo. And you can see that the bounce lost cone pitch angle, I think, is around like 66 or 67 in this run, and that it is not a discontinuity, that there is some slope gradual decrease to zero away from the lost cone. And then lastly, we will be unable to resolve pitch angle dependent lifetimes because of the bounce lost cone data set that we have. We have no pitch angle information. So just to kind of reiterate our science questions, but now accompanied with our methodology, we will be calculating electron lifetimes from LEO and comparing to previous estimates from diffusion coefficients and in situ measurements. From our global maps, we will bin flux by L shell and energy and average over longitude. This will give a time series of flux for a given L shell and energy, just like the Claude Pierre in 2020 A study. And we will calculate lifetimes in a similar methodology. Claude Pierre did use daily averages, and as I mentioned, we are using 12-hour interpolation windows, and so we will have the freedom to expand those interpolation windows, include more reach and POES data if 12 hours is too short. We are looking to calculate a global estimate of the precipitation loss fraction. So integrating over each global map will give an estimate of the total number of precipitating electrons. And we can divide this by the total radiation belt electron content, or the Trebek parameter, which is an estimate of the total number of electrons in the radiation belts. Trebek is a triple integral over the phase space density of the three adiabatic invariants. And you can adjust those limits of integration, which will allow you to isolate different regions of space and different energy electrons. The Murphy study in 2018 uses to track seed relativistic and ultra relativistic populations during a geomagnetic storm. So the variance with L shell and energy can be studied. And the Trebek parameter is quite useful to look at global radiation belt activity. And we plan to provide a baseline of the precipitation loss fraction for which event-specific studies can compare to, and to get the first global estimate. Lastly, we are interested in what is the radiation belt electron precipitation contribution to the radiation environment at aviation altitudes. Our group has developed ionization rate and radiation dose rate lookup tables, and these take as input the precipitating electron energy spectrum in both energy and pitch angle, and output altitude profiles of each quantity down to the surface. We can then calculate a global map of the radiation dose rate at aviation altitudes due to precipitating radiation belt electrons, which would be the first comprehensive quantification of this contribution. And with that, I'd just like to thank everyone for listening today, and I'm happy to take any questions.
All right, thanks so much, Alex. Very informative talk, and I was keeping an eye on the chat here, so feel free if anybody does have some last-minute questions to type them in. But one question I actually had, if you wouldn't mind, I think it's around slide 14 or 15. I believe there was you showed kind of that global map of this electron precipitation, and I think you could definitely see, the South Atlantic. Yeah, this one here. There's clearly the South Atlantic anomaly region, and then I was curious. Actually, maybe one more slide further forward a little bit to then. Yeah, one more forward as well, where you could see kind of the red. That I think the colors were like you could see the flux in red. So maybe one more forward. So I'm sorry, forward I meant backwards. Like maybe 16. Was it slide 16 or something? 16. Let's see. One more, a couple more. A little bit further. Yeah, here we go. Yeah, this is the one. Yep. Yeah, I just thought this showed some of the spatial variability really interesting. So for instance, are those the stripes at the top? I assume they're near like the auroral ovals. And I wondered if there was any reason for the spatial variability along those stripes, right? There's kind of sort of a enhancement maybe from like -150 to 0, but then it gets a little bit more dropping out, say, on each of the plots are around 100 or 120. I didn't know if that was a feature of just that particular time interval, or if it was something that was averaged together, or just curious about that variation.
Yeah, I think this plot is highlighting that all spatial variability in this data set is not due to true precipitation variability. And that this plot is trying to highlight that the top plot is the northbound passes and the bottom plot is the southbound passes.
Okay.
And
got
so
it.
the pitch angle distribution you're measuring is different between those two. You're sampling a different part of the distribution. And so that's going to just appear as spatial variability when it in fact is not. And so part of what we're working on is correcting for that. So around 0 and 60, if you can see my cursor, I'm just kind of circling it. Yep. My guess is that this radiation precipitation region is too small, and that it's probably more something like the southbound plot.
Okay.
And that these stripes in the radiation belts are just due to orbital artifacts.
From the orbits, yeah. Okay. Okay, great. Yeah, thanks for explaining. Well, with that, if there aren't any further questions, I know we went a little bit over time for everybody, but certainly thank you all for attending and had some great early career presentations for this week, and we'll look forward to next time as well. So yeah, thanks again to our speakers and for everyone for joining. Hope you have a good week.
Thanks. Bye-bye.
Bye.